I realize I should give you some real problems for circular motion because that was what you were having the most trouble with, at least based on what you told me. So here are a couple problems we'll do, hopefully quicker than the last two videos. So let's say you are a highway engineer and you have some specifications for a road that you're building. Let's say it's on a flat surface, nothing crazy is going on. So this picture is a road that's curving to the right. It could curve to the left, it doesn't matter. And you are, you know that the road is going to have, or this curve is going to have a radius of 250 meters. You're looking down at this from bird's eye view. Now, you have to decide what is the speed limit going to be on this road. As an engineer, you, who's actually designing things that will be used by people, you need to have a significant safety factor. And so what you're going to assume is you're going to assume the maximum centripetal acceleration a car's tires are able to generate via friction and everything with the road is going to be g over 2. Most tires can do a lot better than that. But you need to account for the person who has not been rotating their tires and has been driving on their tires way after they're legally allowed to drive on those tires. If you look in your tires, by the way, you have treads and there are going to be little raised parts in the tread, like inside the tread. Once the surface of the tire is at the same level as that raised part, you're technically legally required to replace the tires. That's what's called a wear indicator. At that point, the tread depth is so low, it's actually, if it goes any lower, it's technically going to be illegal to drive with those tires on the road. Of course, that's never checked by anybody. And as that happens, your tires are going to lose grip. It's not actually because the rubber's wearing out, by the way. It's because you're putting the rubber through a lot of heat cycles. When you drive the car and then stop the car, then drive the car and stop the car, those heat cycles harden the rubber, and that's why tires actually lose grip. It's not because the tread gives you grip in the dry. Tread allows you to have grip in a condition that's not ideal, like in the snow or in the wet or in gravel or something like that. And that's completely unrelated to this topic. So anyway, you assume that there are going to be people who are irresponsible, not maintaining their cars. So that's what you're going to assume is the maximum value. And you want to have a safety factor of 2. So you want to design this so the speed limit is considerably lower than the maximum possible speed. So we're going to design this for a centripetal acceleration of g over 4. Now g is 9.8, so our acceleration is going to be approximately 9.8 divided by 4, 2.45 meters per second squared. And this turns out to, I think, be pretty okay because on a highway or freeway, you typically want to be able to maintain high speed, so you're not going to want to have a whole lot of centripetal acceleration. So you can maintain those high speeds. So our question is, how fast can we go? So AC equals V squared over R. We know R, in this case I'm going to make it a capital R because it's a specific R. Lowercase r tends to be when R is a variable. Here it's a specific value. And so we need to solve this for V. So multiply the R, take a square root. V is going to be the square root of R times AC, or AC times R, however you want to write it, is fine. Square root of 250 times 2.45. And actually, I think it's going to be way too low. But these numbers are just made up. The purpose isn't to get realistic numbers, because I think the radius is way too small for a highway. Times 2.45. And we get, actually that's not too bad. We get 24.7 meters per second. That's about 25 meters per second. That's about 55 miles per hour. So that is a little bit low, but it's within the realm of reason. So there you go. That is how you do a simple application of using centripetal acceleration. Now here's a second example. So here we've got the Earth and we've got the orbit of a satellite. And I wrote out a couple things here. So for one, this is a satellite it's not supposed to be a double TIE fighter, it's just a satellite. The altitude is often going to be given to you in problems, and that's kind of tricksy because the radius is always from the center of the circle. So you have to add the radius of the Earth, or the radius of the Moon if you're orbiting the Moon, or the radius of the Sun if you're orbiting the Sun, or whatever it is you're orbiting. You have to add that radius to the altitude in order to get your R for your centripetal acceleration or your gravity or whatever it is you're doing. And here that's tangential acceleration, or that tangential velocity, is often going to be called orbital velocity for obvious reasons, because it's orbiting the Earth. So now, time is really important for orbits. The time it takes to complete one full orbit or one full revolution is called period. And we call period, the variable rather we use for period is a capital T, because period starts with a T. And velocity is equal to distance over time. Well, the distance in a full revolution is the circumference. And then, of course, the time is going to be the period. The reason it's a capital T is because it's a specific time, by the way. And, of course, we know circumference is 2 pi r, where r is going to be the radius of the body we're orbiting plus the altitude. And then we get t. So if you wanted to solve for t, multiply the t up, divide the v orbital down, you get t as 2 pi r over v. Now, in the last video, I introduced this concept of angular velocity. However, I didn't relate it to linear velocity, or rather, I should say tangential velocity. This is how these two are related to each other. I mentioned this is in radians per second. That's what makes this equation work. If you do degrees per second for this equation no longer works. You have to do all kinds of annoying stuff. But if you use radians, you just multiply your radius of your circle times your angular velocity, and you get your linear velocity or your tangential velocity. It's all very nice. And that makes sense, right? Because let's say we travel from this line to this line. And let's try to make the radii more or less, the distance is more or less the same. So if you are way out here at this big R, you've traveled this big arc length right here. If you are way down here, you travel this much shorter arc length. Well, it's because you are at a smaller radius, right? So if you're at a smaller radius and you take the same amount of time to sweep the same angle, you have the same angular velocity, you have a different radius, you're going to have a different velocity. Out here, you covered a bigger distance in the same time than you did here. So this is going to be a bigger tangential velocity to cover this longer arc in the same time with the same angular velocity. So that's where that equation comes from. And so if we kind of substitute that in here, v is r omega, well, the r here cancels out with the r next to the omega, and you get that period is 2 pi over omega. And so again, period is the time it takes to complete one full rotation. For reference, frequency, sometimes given as a Greek nu, but typically I just use a curly f, and I think most sources do. That's going to be 1 divided by t. Right? This is how many full rotations per second. This is seconds per full rotation. Rotations per second, seconds per rotation. So the unit for frequency is 1 over seconds, or that's also known as hertz. By the way, these square brackets that I put on the units, that's not a universal thing. That's just something I do to make it very clear that these are units I'm talking about. So 1 over seconds is defined as hertz. So you could technically say that an angular velocity isn't radians per second, it's hertz, because it's really inverse seconds, because radians aren't actually a unit, and inverse seconds is hertz. So anyway, what could we do with this? We could say, all right, well, let's say we look out into the sky and we track some satellite that's orbiting the Earth. And we see that it's got a period of, let's say, 90 minutes, approximately an hour and a half. And let's say we know its altitude is equal to approximately 500 kilometers. What is its velocity? Well, we can just use this stuff right here, and we could also find its centripetal acceleration afterwards. So to do this, we're going to say, okay, we're going to solve this for velocity, which we actually have right there. So velocity is 2 pi r over t. In this case, r is actually going to be the radius of the Earth plus our altitude divided by our period. Now, our period is not 90. That's an easy mistake to make. We have to do period in seconds. 90 times 60. 90 times 60. That is 5,400 seconds. And of course, this is 500,000 meters, or 500 times 10 to the 3 meters. We have to use meters. And the radius of the Earth is 6,371 kilometers. So 6,371,000 meters, approximately. That's the average radius of the Earth. It's a little bit bigger, 6,379 or 8 kilometers at the equator, and a little bit smaller, 6,300, I think 59 or 58 at the for the polar radius. So we plug those numbers in, and we get our answer for the velocity, and it's going to be pretty high. So we're going to get about 2 pi times 6371000. You could, of course, use scientific notation here, plus our altitude is 500,000, all divided by our time is 5,400. Plug all that into your calculator. 6371000 plus 500,000, all divided by 5400, and we get approximately, running out of space here, so we're gonna move that over here. So our orbital velocity is approximately 7,994.77 meters per second. So I'll say 8,000 meters per second, or 8,000 meters is 8 kilometers. So I'll say 8 kilometers per second is our orbital velocity. Very fast. For reference, by the way, this information is approximately correct for the International Space Station. At least that is. I think its altitude might be about 500 miles, not 500 kilometers. I didn't look that up before I started this. So about 8 kilometers per second. Now, if we reduce that altitude in order to maintain the same period, if we reduce this, we're going to reduce r, so we can reduce velocity. If we want to maintain the same period. Of course, in reality, we wouldn't, because gravity is what determines your orbital velocity based on your altitude. Now, we could also figure out the centripetal acceleration. So that's v squared over r. So that's going to be 8,000 squared over the sum of these two, which is 6,000 or 6,871,000. And we add this number and this number together. And so I'm going to use my proper number for my calculator, so for the speed. So square that divided by 6,871,000, and we get approximately 9.3 meters per second squared, which is definitely way too high. So I definitely have this altitude too low for the International Space Station. I think it's actually about 8 or 7.8 or something like that. But what is this acceleration in G's? In order to get acceleration in G's, that's a common unit for acceleration in certain contexts. Just divide whatever acceleration is in meters per second by 9.8. So it's about 0.95 G's. All right, so you're at about 95% of acceleration due to gravity at the surface of the Earth. So that's that. How much time have I been going? Okay, 15 minutes. I'm going to give you one more. If you want one, if you want it, you can just stop the video right now if you don't want it. But here is another one. So let's say you're in a car or something. And you're going over a hill. Let's say the radius of this hill is r equals 50 meters. And let's say down here, we've got r equals 75 meters. So this is a more gentle hill than this one is, or this isn't a hill, this is a dip. This dip is more gentle than the top of this hill is because this has a smaller radius. So what if we want to say, well, what's the maximum speed you can go over this hill and not lose contact with the road? So let's find the, did I say minimum? I meant maximum. What is the maximum speed at which you can go over this hill and not get air? Well, when you're going over the top of the hill, well, what keeps you down? It's gravity, right? So and when you're at the top of the hill there, let's say that's you at the top of the hill, the only acceleration is straight down, and it's gravity, which is equal to 9.8. This is an acceleration, this is not a force diagram, this is just an acceleration. So this is going to be your centripetal acceleration. Your velocity is going to be that way, right? Because you're going, don't worry, at the very top of the hill. When you're over here on the hill or over here on the hill, things are much more complicated. You'd have to take all kinds of angles into account. We're not going to deal with that. So gravity is going to be your centripetal acceleration. Interesting. So if you get to a point where, so as you're sitting in your chair right now, or where we're doing whatever it is you're doing, all of the acceleration due to gravity is just smooshing you into the ground with a force equal to your weight. But as you go over a hill, you may notice, and I'm sure you've gone over a hill before, you feel a little bit lighter at the top of the hill, especially if you're going fast. That's because some of this gravitational acceleration is going into making you turn. And so that portion of gravitational acceleration is not smooshing you into the ground, or in this case, in the seat of your car. So you feel lighter, because the amount of weight that you feel like you have is not actually the force of gravity pulling you down. It's how hard whatever you're standing or sitting on is pushing back up on you. So what if you go so fast that every bit of gravity is necessary just to make you take the turn? All right, such that if you go any faster, gravity's not strong enough anymore, and so the radius is actually going to have to get bigger, right? So if this can't get any bigger, but this is getting bigger, this is also going to have to get bigger in order to keep this at the same value of 9.8. So then you go like that, and oh my goodness, you have achieved air, and you're going to crash, and your car is going to explode. So we don't want that to happen. We know how fast you can go. So at your maximum speed, your centripetal acceleration will be equal to g. This is only true at that maximum speed where you will just barely feel weightless. Your tires will be in contact with the road, but just barely. They won't be exerting any force on the road. They're just going to be barely in contact. You will feel weightless. What's that going to be? So centripetal acceleration is v squared over r. So we just solve for v. This is going to be v max. Is going to be square root. We multiply the r up. We take a square root. And our centripetal acceleration is actually going to be g in this case. And our r is at capital R because it's that specific r. Doesn't really make a big... Is it really a big deal if you use a capital R or lowercase r? No, it's really not. And that's going to be approximately 9.8 times 50 under a square root. Square root of 9.8 times 50. You get 22.1 meters per second, which is about 50 almost 50 miles per hour-ish. By the way I quickly go from meters per second to miles per hour is in my head. I multiply by 2 and then I add about a quarter, because 1 mile or 1 meter per second is about 2.24 miles per hour. So 49.6 miles per hour approximately. So about 50 miles per hour for this particular hill. It's a pretty sharp hill. Now I could do the same thing for here, but this time I might say, well, how fast will you have to go? Actually, you know what? Let's say you maintain that same speed of 22.1 meters per second. How heavy will you feel at the bottom down there? Well, you always have this g acceleration pulling you down, but at the bottom there now your velocity is going to be, we can do it here. If that's your velocity, your centripetal acceleration has to be toward the center of the circle, which is directly above you. So that's going to be your centripetal acceleration. I'm not going to call it centripetal acceleration. I'm going to call that acceleration upwards. Your upward acceleration. Because if you'll notice, gravity is fighting against your upward acceleration. So your centripetal acceleration is actually going to be the net here. So we're going to have to find your upward acceleration and subtract 9.8 from that, and that's going to be your centripetal. All right, so centripetal acceleration here is going to be your acceleration up minus g. And this is going to be what you feel. This is going to be kind of like the weight that you feel. You know what? I usually don't do this problem in terms of acceleration. I usually do this in terms of forces. So let's see. Is this getting too confusing? You know what? Scrap this. Because I only want to talk about accelerations for now. I think this problem is much easier to understand if you have forces. So we'll talk about that later on after we've talked about forces. So hopefully these 3 problems have been useful for you, and it's been 22 minutes. Geez. Sorry for taking so much of your time.